In Unit 7, we're going to start looking at two variable relations, two variable statistics. Everything we've done up till now has been one variable statistics, things that we could calculate the mean, median, and mode of, things that we could do a one variable graph of normal distribution, just different types of distributions. Now we're going to start looking at how two variables, statistics, things can affect each other. Now we've done a lot, you've done a lot of two variable relationship things before in previous math courses. So some of this is going to seem pretty, maybe even more familiar to you than the one variable stuff. But of course, we're also going to be learning new things as well. So let's just jump in with our first lesson, 7.1, which is scatter plots and linear correlation. Does smoking cause lung cancer? Is job performance related to the marks that someone got in high school? Do pollution levels affect the ozone layer in the atmosphere? These are relationships. Smoking and lung cancer, cause and effect, possibly, but maybe not even cause and effect. Is there more lung cancer with more smoking? Is there more better job performance with higher marks? So we're looking at how these things, two different variables, connect to each other and affect each other. In the real world, answers to questions like this are not clear-cut. And inferences have to be made from large sets of data. So two variable statistics provide methods for detecting relationships, so it helps us see if there actually is a relationship between variables, and for seeing how strong those relationships might be, and then we can develop mathematical models of these relationships. Visual pattern in a graph or plot can often reveal the nature of the relationship between two variables. In other words, the first place you should always start is by looking at a scatter plot, because just a visual of that is often enough to let you get an idea of what's going on. When a change in one variable is accompanied by a proportional change in another variable, the variables share a linear correlation, all right? So again, linear correlation just basically means that there is a straight, there's two words here, and they each have different things associated with them. So I'm going to focus on them one at a time. So proportional relates to the word linear. Proportional means that they can be associated with multiplication and division. So we're not adding or subtracting, it's strictly multiplying. So again, think of back in grade 9 when you learned about linear relationships, you thought about slope. Slope was a multiplying factor. And if something just goes up and down by that slope, then it's going to cause a linear relationship. So that's the proportional part. And then when one variable changes in a way that we can see in a pattern compared to another one, then that's where the correlation part comes in, all right? Change in one variable accompanied by a change in the other variable, and the proportional is the linear part, then that's just correlation. The reason why proportional matters is because there's different types of correlations. There can be linear, which forms straight lines. There can be quadratic, all the different things that we've looked at, like exponential, trigonometric. All the relationships can have correlations. So that's one thing. Another term not another term, but the variable or what we're going to represent that with is R. All right, so we're going to use this letter R to represent our correlation coefficient. It's a measure of the strength of a linear correlation between two variables. So to put it in different words, we're going to be given this R value, and it's going to be something between -1 and 1. That's the range of values that R can take on, and that tells us how strong the relationship is between two variables. So it's a continuum. So we have -1, and that's represented by this graph, this number line. You can see -1 on the far left, you can see +1 on the far right, and then there's this continuum running between them with 0 in the middle. So let's start with the positive side, because the negative side is just a variation of that. Let's start with 1. So if something has a R value of 1, that is a perfect positive correlation. Think of 1 in terms of percent. Again, think of these numbers as if they're percents. 100% correlation, a correlation value of 1 means there's a 100% correlation. In other words, it's perfect. So things go step by step exactly. If one variable changes by a little bit, then the other variable will definitely change by a set amount, and we can predict it perfectly. Graphs like this, graphs of this, will look like perfect straight line scatter plots. And I should be able to draw a perfect straight line through this scatter plot and hit every single one of the points in the case of a perfect correlation. So something like that. Don't worry about the slope. The R value's got nothing to do with the slope of this graph. I could have made it a lot steeper. I could have made it less steep. It's just that I'm hitting every single one of the points. That's what makes it an R value of 1. But there is one thing that's similar to slope as far as we go here. If it is going upwards to the right, like this one is, that's where the positive part comes in. So again, R value is not slope, but the one attribute that it does share with slope is that if it's a positive R value, it's going up to the right. If it's a negative R value, it's going to go down to the right. And so that leads me to maybe jump to the other end of the line where we've got -1. This is still also a perfect correlation, but it's a negative correlation, which means that I'm still going to have my points in a perfect straight line on a scatter plot, but now they are going to go downwards from left to right. And again, the correlation has got nothing to do with the steepness of the line. It is strictly 1 means perfect correlation, all lining up, and the negative part for -1 means that it's going downwards. 0, let's go to the middle here now, means no correlation whatsoever. Think of two variables that have got nothing to do with each other, and you just have this scatter plot which has got no pattern shown whatsoever. That would have an R value of 0. So just to pick some random ideas that come to my mind, if I was to do a scatter plot of the various heights of people at Uxbridge Secondary School and compare them to a random sample of people's income in Bangladesh, I would not expect to see some relationship between those two things. There's nothing whatsoever. They're different countries, they're different measurements, there's no reason to have any correlation between them. I would expect to have a correlation value, an R value, somewhere near 0. All right? And then, as I said, it's a continuum. So the closer we get to 1, the stronger it is. So we consider anything between 0.67 and 1 to be strong. We consider anything between 0 and 0.33 to be weak, and anything between 0.33 and 0.67 to be moderate. So it's just dividing it into thirds. And it's the exact same on the other side, it's just we're dealing with negative correlations. And again, all that has to do with is the graph, is it going to be positive or negative? Another way we can talk about this is we could call this a direct relationship. We could call this an inverse relation, whereas one, in this case, as one value goes up, the other one's going down. But still, everything's linear. Okay, so that's the idea of R value. As I said earlier in this lesson, we should be able to, the first thing we should be able to do is look at the scatter plot and just estimate what the correlation is. So here we got some scatter plots with R values underneath them, but try, if you can, to ignore the R values shown. And maybe I would have been nice if I'd covered them up first, but I haven't. You've seen them. And just from looking at the graph, decide if something's weak or strong, positive or negative. All right. So the first one, the lines are all tightly, or the dots are all tightly grouped together, and they're heading in a downward direction from left to right. So it's negative. Definitely the first thing that jumps out to me is that it's negative, but that it's strong. So it's not perfect. My line isn't touching some of the dots. As you can see, it's touching some of them, but even the dots that it's not touching, they're all very close to the line. So it's a strong correlation. And as you can see, the R value is negative 0.96, so that confirms that. For the next one, again, negative is definitely going downward from left to right, but it's a bit more spread out, so I'd call that one moderate negative. As you can see from the R value shown, it's at negative 0.602, so it's getting close to the cutoff between moderate and strong. If the dots were just a little bit closer to the line, then it would bump up into a strong relationship. And this one, still, you can see a trend generally going down, though. The trend, the scatter plot is definitely getting harder to see a pattern going on, but this one would be a weak negative. And then I can see a general trend going upwards in this one, so it's strong, it's positive, but it's weak. And then the next two should be pretty obvious by now. This one's getting a little bit stronger, so we'd call that one moderate. Again, it's 0.66 when you look at the R value given, and that's pretty much borderline. You could make an argument that that's very close to being a strong one, but it's obviously not as strong as this one is. Strong. Can't read my own writing. Positive. Again, it's a continuum. So we could have different ones that go in between any of these examples here. So that's all well and good. Looking at a scatter plot, deciding whether it's positive or negative, deciding how strong it is, are good things to just sort of ballpark. We eyeball them and say, okay, yeah, that's my estimate. But if we want to actually calculate the R value, where does that come from? There is a calculation for this. This is the formula, and it looks horrible, but it isn't actually that bad. We know all the different parts that we can put in here. We just have to, it involves a few different numbers. So again, here's the formula, and we know that that the sigma here, this symbol here, just means to add things up. So this sigma xy simply means x and y are just the variables. Again, everything we do from here on out is going to be two variables, so x and y are just our two variables. And so we're going to multiply x times y. Think of an ordered pair. We're multiplying the x and y coordinates of an ordered pair together. And then we're going to have a bunch of ordered pairs. So we're going to multiply all those x and y's together and add them up. That's exactly what it's telling us. For the next part, we've got we've got sigma x, and that just means add up all the different x values. And then we've got sigma y, which just means add up all the y values. N, by the way, is simply our number of pieces of data. Might as well identify everything right here. And then on the bottom, what we have is, again, sigma x squared. What is that telling us to do? Well, that's just telling us square each of our x values and then add them up. Whereas we know order of operations makes a difference. This one, let's do it in a different color. This one is saying add up all the x values and then square it. So order of operations makes a difference, right? Again, sigma y squared means square the y's, then add them up. Sigma y all squared means add up all the y's and then square them. So here we have all these different variables, different things that we can do with them. I'm going to keep this highlighting here, but I'm just going to show that this is really the same as this, but then on the bottom we square it. And I think I used this color. This one is the same as what's on the top, but on the bottom we have to square it, right? So let's look at an actual example. A farmer wants to determine whether there is a relationship between the mean temperature during the growing season and the size of his wheat crop. He assembles the following data for the last 6 years. That means that n is equal to 6. Create a scatter plot of these variables and indicate any linear correlation between the two variables. All right, so that's down here. So just in order to make everything fit on the page, sort of got a bit creative. So we're going down to plot this, and we're going to use these ordered pairs here. Every one of these, again, think of them as ordered pairs. So temperature is our x, it's on our horizontal axis, and yield is our y, that's on our vertical axis. The scale's already been laid out for you. All right, so if we want to graph these points, we had 4 and 1.6, which would be about here. We had 8 and 2.4, which is up about here, and so on. I'm just treating these like ordered pairs. The next one was 10 and 2.0. Then we went back to 9 and 2.6, and 11 and 2.1, and finally 6 and 2.2. So there's my scatter plot. And again, from a visual, looking at this, it definitely looks positive. I would not characterize it as strong positive. It's definitely not perfect. There's no way I can draw a straight line and hit all those points. My best feeling from this is moderate and positive. Now I feel very strongly about it being positive. The moderate part, with only 6 pieces of data, it's kind of hard to be as confident with that. But I still, that's what I'm going to predict. All right, part B, compute the correlation coefficient. So we have to use this formula up here. So the reason why I highlighted things in these different colors is so that, just to hopefully make it easier to see that we can add these things up. We have, let's see, just trying to match up the colors before I go any further. So sigma x squared I did in yellow, sigma x I did in green, sigma y I did in orange, sigma y squared was blue, and sigma xy I did in pink. Okay, so obviously I'm going to have to fill in some values from this table. the table, you don't need the table, but it really makes things a lot easier. So I'm gonna have to add up a lot of things, and the table makes it easier. So the first, adding up all the x's, just add up what's in that column, and when I add those all up, it turns out to equal 48. When I add up all my y's in that second column, it works out to be 12.9. If I want to get the values that go in the third column, all I do is square my different x's. So 4 squared is 16, 8 squared is 64, and so on, right? So that's not hard to do. 100, 81, 121, 36. And when I add those up, I get 418. And then when I want to get my y squared, I'll just square these guys. And so I'll get 2.56. 5.76, 4.00, 6.76, 4.41, and 4.84. And then adding all those together is 28.33. And then finally, xy just means multiply x times y. So 4 times 1.6 is 6.4. And 8 times 2.4 is 19.2. And so on. 20, 23.4, 23.1, and 13.2. Adding it up, I get 105.3. So a little tedious, not hard. Then we put them in the appropriate place in the formula. So I'm going to take this formula and I'm going to start filling things in. So r is going to equal n, which was 6, times sigma xy, which is 105.3, minus sigma x, which was 48, times sigma y, which was 12.9, all over the square root of n, again 6, times sigma x squared, 418, minus sigma x, and then square it, so that was 48 squared, then 6, 28.33, which was sigma y squared, minus sigma y all squared, so 12.9 squared there. All right, so filling in the numbers again, kind of a tedious piece of work to do, but not that big of a deal. Now that I've got them written out, I can zoom in a bit. So simplifying a bit, I get 631.8 minus 619.2 over the square root of 2508 minus 2304. Again, just doing a bit of the work here, simplifying it, taking in stages, in other words. 169.98 minus 166.41, giving me 12.6 over 26.99. Again, I've worked this out ahead of time. Obviously, I'm not typing in my calculator right now, but I'm pretty sure this is correct, 0.467. So that's my R value. So a lot of work, all right? But now we have confirmation, because when we looked at the graph, I suggested it was moderate and positive. Definitely moderate. Definitely positive. And the R value I got was positive. And moderate is 0.46, which is close to about 0.5. So going back to our scale here, it came in about here, doesn't it? Right about in the middle of moderate. So just to finish off this question then, what can the farmer conclude about the relationship between the mean temperature during the growing season and the wheat yields in his farm? Save time, I filled this in ahead of time. It looks like crop yield increases somewhat as temperature increases, somewhat because it's moderate, 4.67. And our value of approximately 0.5 is moderate correlation, meaning there are probably other factors involved as well. In other words, the temperature isn't the only thing that affects crops. There's the amount of water that the crops get. There's insects. Depends on if there's any major storms. There's lots of things in the real world that can affect things. So that's why it's only a moderate relationship. But definitely it indicates that the temperature has some bearing on it. The other thing that we can't assume, though, although we could probably guess that it probably is an effect here, is cause and effect. In a later lesson, we're going to talk about cause and effect. Does one variable cause another variable to happen, or are they just, is there something else going on? But that's not for today. Right now, we're done.